So today we're going to be talking about inverses. So the topic though is Common Core. It is F for function and IF for interpreting functions. And we're going to relate domain of a function to its graph and inverse. Okay, write that down. So the Common Core is FIF, which is functions. Interpreting functions relate domain of a function to its graph and its inverse. Okay? So first of all, example 1. We want to determine if the functions are one-to-one and if they have an inverse. So if you know a little bit about the graph, and if you don't, you can just graph it. But x cubed, we can actually graph using our brains because we're so smart. So we'll do a t-table in our brain. So if I start at 0, what's 0 cubed? 0. If I go over 1, what's 1 cubed? 1 times 1 times 1, right? If I go over 2, it's 2 cubed. Don't say 6. 2 cubed is, don't say 6. 8. 1, 2, 3, 4. So it's up here. 3 cubed is 27 and so forth. Okay, now, negative 1. Negative 1 cubed is? Negative 1. Negative 2 cubed is? Don't say negative 6, please. Negative 8. So this graph looks something like this. Is it one-to-one?
Yes.
Yes, because it passes our vertical line test. Yes. Does it have an, boys, does it have an inverse? Yes, it has an inverse. If it's one-to-one, then it has an inverse, okay? Okay, B. So start at negative 4, 1, 2, 3, 4. It's a parabola. If you didn't know that, then you should. Easy way to graph the parabola is go to the vertex, negative 4. 1 squared is 1. 2 squared is 4. 3 squared is 9. But we know it's symmetrical, right? We know it's symmetrical on the other side of the y-axis. So I went 1, 4, 9. So I'm also going to go negative 1, up 1, go back 2, up 4. And I get a graph that looks like this, okay? Right? So, is it one-to-one? No, it fails the horizontal line test. No. Does it have an inverse? No. Okay? Easy? Right? Okay. Letter C. Square root of graph?
Just square root of 0.
Yeah, square root of 0 is 0. If I go over 1, what's the square root of 1?
1.
I'm going to go over 4. 1, 2, 3, 4, because the square root of 4 is 2. I don't need all the numbers in between because they're decimal answers. And then I go over to 9, up 3, and it looks like this. I will not go back because that's negative square roots. The graph does not exist back here because you can't have square roots of negative numbers. So that is it. So even though it's cut off, is it one-to-one?
Yes.
It is. It does pass the horizontal line test. Even though it's cut off on the back because you can't have negatives, it still is one-to-one. So yes, it has an inverse. Okay, now let's take a look at example 2. Example 2 is really this parabola here, right? Example 2 is really that graph right there. Now let's change the domain to make it one-to-one. So what we have to do is this. We have to get rid of half the graph. Now this is math. You can't just erase it. Shh. Listen. You can't just erase it. You have to mathematically erase it. So we're going to change its domain. So we're going to put this little stipulation in this problem. We're going to say let x be greater than or equal to 0. All right? If we do that, then I can take my white out and get rid of this half the graph. If you don't have white out, use your eraser. And if you use pen, scribble it out. Now, what we did is we changed the domain to make it work. Now, you could have also taken the back half, but most of the time, most of our applications are positive things. So we get rid of the back half by making this stipulation. So we're saying go ahead and graph this, but make sure when you graph it, you only keep the part that's greater than or equal to 0, which would be this half the graph. Okay? So I made a domain change, so I'm going to look at the positive part of the graph. Now, it is one-to-one, isn't it? Right?
Yes.
So it has an inverse. Now it has an inverse, but the inverse has to have a domain change to work. All right? All right. Example 3. f of x equals 3x plus 4. So let's graph the graph and its inverse. So I'm going to start at 4. 1, 2, 3, 4. And I'm going to go up 3 over 1, but I'll go down 3, back 1. Right? So I'm just graphing this line. Okay, that's my 3x plus 4. Right? That's f of x. Now, we are going to find f inverse by switching x, y points to yx points. Okay, now it's really easy, but you got to pay attention. Super easy, but you have to pay attention. Okay, so let's just go and start right here at this point. So this point really is the point 0, 4, right? If I switch 0, 4, it becomes 4, 0. So the inverse would be at 1, 2, 3, 4, 0. So I switched 0, 4 and made it 4, 0. It's that easy, okay? This point right here is at negative 1, 1. I'll use the right color. Negative 1, 1. If I switch it, I get a 1, negative 1. So I just switched this point, made it 1, negative 1. Okay. This point right here is at negative 2, but that's pretty easy. If I switch negative 2, it becomes negative 2. You agree? So it's right on top of the line, right? Okay, this point up here is at 1, 7. 7, 1. Okay, so 7, 1 is right about there. So now I'm going to go ahead and draw in my inverse. Okay, there's my inverse. That's my f inverse of x. Okay, now one of the things I put on here that I want you to see is I said graph y equals x. Okay, I want you to graph y equals x. So how do I graph that line? It is 1 over. Good. Keep going. Yeah. What's the starting point? Nice job. Yes. Where do I start? 0. Yep. So start at 0, up 1 over 1, up 1 over 1, up 1, just like Wyatt said. All right. Okay. So the line y equals x is the line of reflection between the function and its inverse. This is my line of reflection, meaning if I were to fold the function over this line, it goes on to its inverse. Or if I were to fold the inverse over this line, like just fold it, like take your paper and just, fold right there. See what I'm doing? Just fold it. So it's a line of reflection over this line. Or think about a barbecue skewer. If you want to think about barbecue skewer, if I rotate it, this one would rotate right under that. Okay? That will happen with every function and its inverse. Every function and its inverse will always be reflections over the line y equals x, which makes sense. That's the line where x and y are equal, right? And that's why this particular point, negative 2, was negative 2, okay? Now, wouldn't it be easier, though, to graph this thing if I didn't have to do point by point by point? Absolutely. So instead of changing x, y, let's change all of the x's and all of the y's. So what I'm going to do is just change y equals 3x plus 4. f of x and y are the same thing, right? To x equals 3y plus 4. I did the old switcheroo. So when I do the switch, I switch x and y. In a sense, because it's the y variable and the x variable, I switched them all. I mean, I switched every single point, right? Now, the only thing is if I want to graph this, if I need to graph this, I better solve for y. Okay, I got to solve for y. Okay, so to solve for y, minus 4 minus 4. Divide by 3, I get a 1/3 x minus 1 1/3 equals y. And sure enough, that kind of looks like the graph I have. Start at negative 1 1/3, go up 1/3, up 1/3, and there is the inverse line. Okay, this is the inverse equation. So what we're going to do with it is we're going to rewrite it as an inverse. We're going to rewrite as f inverse of x equals 1/3 x minus 1 1/3. That's my inverse equation, which corresponds to the inverse graph that we drew, okay? Thumbs up? Okay, so recap real quick. To do an inverse, I switch x and y's, right? In order to find the equation, same thing, I switch the x and y's. And then solve for y, okay? Turn the page. All right, example 4. And use pencil, please, because you're going to need to erase, all right? So we'll go back to this one. We're going to go back to this parabola. Start at negative 4. 1, 2, 3, 4. It's a parabola. 1, 1, 2, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4, 5, 6, 8, 7, 8, 9, right? I'm just doing 1 squared, 2 squared, 3 squared. That's how I do my t-table in my head. We know it's symmetrical over the y-axis, so I'll have it on the other side. Okay. And I draw in the parabola, okay? Now, well, normally you erase the backside. You don't have to, but I will normally, because most applications are positive values. Does that make sense? Okay. It would not be wrong to get rid of the front half. It wouldn't be wrong at all. But most of the time we'll get rid of the back half, okay? So, again, this is not one-to-one, is it? So we're going to fix it. So we need to change the domain. So if we change the domain, let's say that x is going to be greater than or equal to 0. So that I get rid of, yeah, so when I say that, I only want the positive half of the parabola, which means the negative half of the parabola doesn't exist anymore, so I get rid of it. Now it's 1-to-1, isn't it? Okay, now it's 1-to-1. So what's the domain? Well, the domain is just x is greater than or equal to 0. Start at an x value of 0, and it goes on forever and ever and ever, right? And the range is going to be y is greater than or equal to negative 4. Start at a height of negative 4 and go up, right? Now let's look at the inverse. So point by point, let's see, let me find a different color. How about blue? Blue will work. So I'm at 0, negative 4, so its inverse will be at negative 4, 0. I'm at 1, negative 3, so its inverse will be at negative 3, 1. I'm at 2, 0, so I'm going to go 0, 2. I'm at 3, 5, so I'll go 5, 3. What I have is f of x. That's my original function. And I have my f inverse of x. Now, what's the equation? What's the equation of this? So the equation of the inverse, instead of having y equals x squared minus 4, right? We're going to make it x equals, right? X equals y squared minus 4. Let's solve for y. So bring over the 4. X plus 4 equals y squared. Square root both sides. X plus 4 equals y. And when we did this stuff in Algebra 2, we took a square from a square root. We got a plus or minus. Remember that? We got a plus or minus? Remember when we got from the x squared to the y squared, we got a plus or minus? Remember that? Plus or minus, because there should be two answers. However, in this case, since we changed it to just greater than 0, it's just going to be the positive, okay? So it's just the square root of x plus 4. Now, we can take a look at that on the calculator if we wanted to, and you'll see it, all right? So here's my inverse equation. So let's write it. I'm going to have f inverse of x is equal to the square root of x plus 4. Okay, that's my inverse equation. Here's my inverse graph. Now, domain. What's the domain of the inverse graph? X is greater than or equal to negative 4. Perfect. What's the range of my inverse graph? What's the range of my inverse graph? 0. Y is greater than or equal to 0. Even though it flattens out, it's always moving up. It is always moving up, but just not at a very big rate, okay? Do you notice anything between the two? So the domain of the function is always the range of the inverse, and the range of the function is always equal to the domain of the inverse, which makes sense. Domain is x and range is y, and once you switch them, you switch the domain and range. Capiche? Yeah, Will?
The faster way of doing it is graph, like the square root of x plus 4 is
Yeah, absolutely. Yeah, absolutely. Yeah, you can use your calculator and graph it. Yeah, I like to do it this way so you can see the point-by-point switch around, but you're totally right, okay? Good, I'm glad you... Now, example 5. Real quick, before we graph this one, I mostly just want to talk about its asymptote. So x cannot equal 1. You guys agree with that? So if we were to graph this, in fact, let's see, do I have a calculator? I'm going to steal yours again. You know, all right, either way. I got this one, it's all right. So let me graph this. So if I were to graph this crazy equation here, something weird's going to happen at 1. Do you remember that from Algebra 2? We're going to get an asymptote. Do you remember that? We're going to get an asymptote at 1. Those of you who just had Algebra 2, if you divide by 0, it kicks your asymptote, remember? So parentheses 2x plus 3 divided by parentheses x minus 1, right? If I graph it, what is this thing here? What's that thing right there? That's your asymptote. That's your asymptote. So when we draw asymptotes, we draw them as dashed lines. They're not part of our graph. They're boundaries for our graph, right? So the graph looks something like this. And the other's way up here, okay? You can go ahead and adjust your window. That's the function. Okay. Now it's inverse. Let's do the inverse real quickly. So the inverse, if it has a vertical asymptote, then the inverse would have a horizontal asymptote because the x becomes the y. So I'm going to have, for the inverse, we're going to have a horizontal asymptote at y equals 1. Do you remember x and y switch places, right? So for the original graph, it has a vertical asymptote at x equals 1. For the inverse, it's got to be just the opposite. It's got to have a a horizontal asymptote at 1. Now, let's get some points. From my graph, I noticed it had a y-intercept of -3, so it's a point at 0, -3. So the inverse would have to have a point at -3, 0, right? Right there, okay. It has an x-intercept at -1.5, 0. So it'd have to be a -1.5, 0. So this one's going to look like this kind of graph, okay? And then the other part of it is going to be up like this. Let me graph it. All right, let me get the equation. I'm not doing a very good job of graphing it. If I can get the equation, I can graph it. Okay, check it out. See how I'm going to graph it, okay? Y equals 2x plus 3 over x minus 1. Switch it. X equals 2y plus 3 over y minus 1, right? Cross multiply. X times y minus 1 equals 3. 2y plus 3. Sorry. Still trying to solve for y, right? So xy minus x equals 2y plus 3. Bring over the x. I won't have you do this unless it's an extra credit problem, but I'm going to do it with you. Bring over the x. Bring over the 2y. I'll have an xy equals, whoops, xy minus 2y equals x plus 3. Almost there, honest. Common factor out of y, x minus 2 equals x plus 3. Divide y equals x plus 3 over x minus 2. That is its inverse equation.
Whoa.
That is a great problem. Like that problem.
You said
Yeah, that would be a good extra credit, wouldn't it?
Yes.
Okay. Do you want me to go through that?